So first, I'd like to thank the organizer of the workshop. I'm Yuzi. Today, I will introduce our work, domain generalization, where adversarial learned level domain. The success of the machine learning algorithm largely depends on assuming that the training data and test data, are independent and identically distributed. However, in reality, this IID, also we call this IID assumption. However, in reality, the IID assumption may not hold. Oh, sorry. Okay. So in this paper, we wanted to improve models performance when the IID assumption doesn't hold. And there are a lot of settings consider this task. In this work, we consider the domain generation task. And also we will introduce in the previous solutions and limitations in these sections, the background sections. Okay, so as I said, in this work, we wanted to improve model performance when the IID assumption may not hold. And in reality, this will happen a lot. This will often happen. One example is like, for example, we can collect the data in hospital 1, and we're using this data to train, for example, a cancer detection models. And when we have such models, we want that the model can be used in a lot of hospitals. For example, we want to apply these models in hospital 2. In these situations, since the hospital 1 and hospital 2 have some difference, for example, the device or patient are different, then the data will have different distributions. In such case, the IID assumption may not hold. And when this assumption didn't hold, the performance of the machine learning models may decrease significantly. Okay. And in this work, we consider the domain generation task to improve models performance when the IID assumption didn't hold. For these settings, in the training phase, the model is trained on the multiple domains, which means, for example, in the following pictures, we have 3 domains: photo, sketch, and cartoon. And in the test phase, we want the trained models can generalize to unseen domain. For example, we test the trained models on the art domains. And I'd like to remark that the art domain will not include in the training domain. So this is an unseen domain for the classifier. And the data augmentation is one of the most common way to solve the domain generation task. And we focus on 2 types of the data augmentation strategies. The first is the adversarial data augmentations. It attempts to augment the training data with difficult samples. And we can also consider these samples are drawn from the worst case distributions. Usually, the previous work used the pixel level perturbations to generate the worst case samples. It's like very like the adversarial attack. And the paper 1 shows that the augmenting the samples from the worst case distributions can improve models' domain generation abilities. However, as the example shows, when we consider the domain generation task, the difference between domains are very large. However, using the pixel level adversarial attack, we can only obtain the samples that with similar semantics with similar styles, as the latter figure shows. The first row is the original training data. The second row is the training data generated by the pixel level perturbation, pixel level adversarial attack. We can see there are no significant difference from the first row and second row. Another strategy is called the generative model-based data augmentation. It attempts to synthesize the training data by generative models. This method often focuses on the increasing the diversity of the training data. As the left figure shows, each figure is one of the training data. We can say the style of the training data can change very differently. And however, the limitation of this method is that this work have never considered the data combinations with the worst case distributions using the generative model. Since the paper one already showed that difficult samples were helpful for the DG task. So in this work, we wanted to combine the advantage from the both adversarial data combinations and the generative model-based method. And more specifically, in this work, we wanted to synthesize images that become more and more difficult during the classifier training. And we want to synthesize the images become semantically different from the training domain. So then I will introduce our solutions. So overall, we aim to control the data generating distributions represented by our generative models, so that it can generate hard samples. And then we want to train the classifier θF with these samples. So the overall objective is showing the following. In the inner part, we want to control the data generating distribution PG, so that the loss value of the classification loss will be maximized. And in the outer part, we want to optimize the θF, so that the loss function, the loss value is minimized. And here, one difficulty is how to control the generative model's behavior, which means how we affect the PG. So our idea is to utilize a specific image-to-image translation models below. So to control the behavior of the generative models, we utilize these below models. This below model is a very special image-to-image translation models, and it's like the following equation shows. For a below model G, it takes two input. It takes two things as input. One is the original image X. One is a domain code, or we call it domain code Z. And output are images X prime that the style specified by the domain codes. In the left figures, we show several samples of the domain codes. These figures all take one sim X is input, but you can see by utilizing different domain codes, the style of the images can be very different. However, empirically, we will find the original below models has some limitations. That is, the original below models can only generate images with limited diversity. And we will use the following simplified examples to explain why this happens. So the below models is built on the cycle-GAN models. The cycle-GAN models is the red. One example of cycle-GAN models is showing on the red figures. Here, the X and Y are two different domains. And we have in these models, these models has four modulars, two generator G and F, two discriminator DX and DY. The generator G can transfer images from domain X to the domain Y, and the generator F can transform the images from domain Y to domain X. In the cycle-GAN models, they have a very special loss functions. to ensure that the generated images can maintain the semantics. This loss is called the cycle consistent loss. The basic idea of this loss is that for when we transform the image X from the domain image from domain X to domain Y, and we can when we recover that transferred image between from domain Y to domain X, the distance between the FGX and X should be minimized, which means we can recover the original images from the transferred images. And if we can achieve this, which means we already maintain the semantics. However, the paper one shows that the cycle consistent loss will limit the diversity of the generated images. Since the DLO model is built on the cycle GAN model, which means this also is the reason that can limit the diversity of the DLO models. Hence, we follow the paper one strategies, use a weak version of the cycle consistent loss to replace the original cycle consistent loss. The main idea of the new cycle consistent loss is that instead of forcing the generated images can be recovered, we now enforce the feature extracted by the discriminators can be recovered. So as this equation shows, this has two terms. For the first terms, we want to enforce the feature level recovery. We want the features extracted by the discriminator dx can be recovered. And in the second term is like the original cycle consistent loss. We force the pixel level recovery. So with this new cycle consistent loss, we find that the diversity of the synthesized images is improved. Is the red figure shows. The left figure is the original DLO models and its output. The red figures is the DLO models with new cycle consistent loss. We can say although the inputs are exactly the same, and the training data is exactly the same, when we're changing the loss functions, the diversity of the generated images can be improved a lot. Also, empirically, we find that improving the diversity is helpful to improve the domain generation ability. Hence, in this work, instead of using the DLO models, we utilize the new models. We call this model DLO-B. And with the DLO-B models, now we can control the behavior of the generative models by optimizing the domain code distributions. And we propose two strategies to represent our trainable domain code distributions. Then, by optimizing these trainable distributions, we can find the worst case data generating distributions represented by the DLO-B models. For these two strategies, the first is we're using our trainable denucleate distributions to represent our trainable domain code distributions. And the second, we're using a neural network termed the domain code NN to represent the domain code distributions. First, I will talk the first strategies, the denucleate distributions. Since the domain code are the k-dimensional probability vectors, so it's naturally to first consider elemental distributions. So we consider the denucleated distributions. So we utilize our denucleated distribution B parameterized by alpha 1 to alpha k to represent the distribution, the domain code distributions. And then we can optimize the domain code distributions by optimizing the alpha 1 to alpha k to find the worst case distributions. And the advantage of this strategy is that fewer parameters need to be optimized. because here the large K is the number of domains. In the domain generation settings, usually the K is not is less than 100. So which means there are very small parameters we need to optimize. And the second strategy is using a neural network termed domain code NN to represent the domain code distributions. Inspired by the GAN, we utilize a neural network small g to represent the domain code distributions. First, we design the last layer of the domain code NN is a softmax layer. That is because domain code is a probability vectors. Hence, to make the output of the G is valid domain code is a valid domain code. So we need a softmax layer. And like the GAN, we take the Gaussian node C as input, so that the output can represent the domain code distributions. The advantage of this strategy is the better representation abilities, because it can represent more, hence it can represent more complex domain code distributions. When the given training domain are very complex, we prefer using the domain code NN instead of the deep distributions. Okay, so now I will introduce our main framework. So with the above idea, the domain, the way to the generative models and the way to represent the domain code distributions, we now propose our data augmentation method, the generative adversarial domain augmentations. Because we have two strategies to represent the domain code distributions. So in here, I utilize one of them to give explanations. So there are three modules in our proposals. The first is the domain code NN small g. And this part is used to represent the domain code distributions. And this module can also be replaced by a trainable dedicated distributions. And second is a trainable pre-trained DLB models. And the third is the mean classifier F. We will use the F to do the classification task. And our mean object function is showing the following. Basically, we wanted to solve the following min-max optimization problems. And to solve it, we alternatively do the inner maximization and outer minimizations. We first maximize the objective with regard to the small g. In this part, we want to find the worst case distributions of the domain code. We find our worst case domain code distributions by optimize the theta g to maximize the loss functions. And then we minimize the objective with regard to the theta f. In these steps, we want to train the models over the worst case distributions. And then we repeat above two steps. Okay, then I will introduce some experimental results. So first, we consider experimental settings that we only have the limited computing resources, which means all general hyperparameters. Here, the general hyperparameters means the type of optimizers, the narrators, and some other parameters that were used in the most of machine learning algorithms. For this general hyperparameters, they are all set as consistent values for all proposals and all commutators. And for hyperparameters that are only needed in all methods, we tune them with limited trials. So this too is because we only have the limited computing resources. And the first experimenter is test all proposals on 3 common benchmarks. And in this page, I first show the result on 2 common benchmarks. One is called the digits DG. This benchmark have 4 different digits dataset. And the second is the PACS dataset. It also have 4 different domains: the photo, sketch, cartoon, and art. And to apply this experiment, we utilize a principle called leave one out principle, which means we first choose one domain is the test domain, and using the rest of 3 domain is the training domain, and train the model and test accuracy. And first, on these 2 datasets, on the digit dataset, all 2 proposals, GDD, that means all proposals with the linear distributions, and GDNN, which means all proposals with a domain code NN, achieve the best performance among all competitors. And for the PSA dataset, all result is close to the state-of-art method, MBDG. And the third benchmark is the Office Home dataset. It also have 4 domains. And also we follow the leave one out principles to apply to conduct the experiment. And I'd like to say in the overall, in average accuracy, our method didn't have some advantages over the other competitors. For example, the Young, and but by comparing the performance of the ERM method, the ERM here, ERM is empirical risk minimizations. By comparing the performance of the ERM on each domains, we can judge the difficulty of each domain. So on the Office Home dataset, the most difficult domain is ClickPad, and on the digits DG, the most difficult domain is MSM, and on the PCS, the most difficult domain is Sketch. We can find, instead of the MBDG on the Sketch domain, on all most difficult domains, all proposals achieve the best result. This indicates that all proposals is better at handling the difficult domains. This also fits the design of all proposals. We want to train the models on the worst case distributions. And also, we visualize all 2 proposals. We visualize the generated images in each steps and the domain code distributions during the training. And is the red figure shows. The top is the result of the visualization result of the GADA, and the bottom is the visualization result of the GADD. We can find the generated images become more and more difficult. Intuitively, that M-list images should be the most easy domain in the digits task. The images become more and more colorful, indicates that the samples become more and more difficult. So this is the first thing we can find in the visualization result. The second is that we can find the GADD is easier to optimize than GADNN. For example, in the step 3000 and 4000, we can find the proportion of the colorful images is larger than the proportion of the colorful images in the GADD is larger than the proportion in the GADNN. And also, we can see the domain code distributions. The GADD quickly converge to a very small space, but the GADNN still on a large space. And also, we check the importance of each modulus in our proposals by the ablation studies. We apply the following ablation studies. First, we test the importance of the generative models. We use a pixel level adversarial attack to replace the generative models. And second, we test we test the importance of the worst case distributions. We're using the non-adversarial distributions of the domain code to replace the learned adversarial distribution of the domain code. So here we're using two distributions. One is uniform distribution on the simplex. One is the logistic normal distributions. And three, we test what happens if we do not use a domain code NN. We replace the domain code NN by adversarial optimizing the domain code directly. Kind of like the adversarial attack, adversarial training. So this here is the result of the application studies, and here we can find the result of the proposals. This result shows that each modulus is important in our framework. Also, the paper one shows that the hyperparameter selections is very, very important for the DG task. Hence, our previous settings that assume that limited computation or computing resources may be not suitable for the DG task. Hence, for the better comparisons, we also conduct an experiment under the settings that we have enough computational resources. And since we have enough computational resources, we first random set the value of all hyperparameters from our uniform distributions respectively. And then we train our models by our proposals, and we repeat this process 20 times. We will have 20 set of hyperparameters, and we evaluate these 20 models on the training evaluation set and choose hyperparameters that achieve the best validation accuracy is our final hyperparameters. And with the fine-tuned hyperparameters, here the F refer to the fine-tuned. We can find all proposals, the performance of all proposals increased very significantly. Also, compared with the state of also all proposal GDA can achieve better performance than the previous state-of-art method MBDG under these settings. Okay, so now to sum up, in this work, we consider a data augmentation strategies that we consider the data augmentations with the worst case distributions using the generative models. And for our proposal JDA, we utilize our pre-trained DLB models whose behavior is conditioned by the domain codes. And we propose to learn our trainable dynamic distributions or domain code NN to represent the distributions of the domain codes. We empirically evaluate our proposals on the different datasets, and the experimental result suggests that the GDA effectively increases the model's generation abilities. Okay, thank you. So, do anyone have some questions?
Okay, thank you very much. Any questions? So let me start. So can you say something about the computation time compared with some basic approaches?
You mean computation time compared with the previous work?
Yeah.
Actually, there are no large difference between our proposals and the previous work the previous method. Maybe the most for the training time, the most of the time will be used to train the DLO models. For when we train the classifier, the time actually you can see the training objective. The training time actually, the training step is same as the previous method. So the training time there are no large difference between our work and the previous work, our method and previous method. And also, in my understandings, so because what we want to solve is a classification task, and the maybe in the understanding of ours, in all understandings, the training time may be not important in this task, because we just want to train a classifier, and this although if the classifier training the classifier takes a lot of time is not acceptable. But for example, 2 hours and 3 hours there are no such difference. Is because the model, the training, after we finish the training, when we test the models, the test time should be the same.
Right. So what about the number of hyperparameters? Are they also the same?
Actually, in our training objective, we do not involve some another hyperparameters. Hence, for the hyperparameters, in our training objective, we only have one hyperparameters to balance the trade-off between the model trained on the worst case distributions and the model trained on original training data. So we do not have a lot of hyperparameters in our work.
So the number of hyperparameters is the same as previous methods, or do you have more hyperparameters?
Because for different methods, they have different number of hyperparameters. Right. I can just say for some method we have less hyperparameters, but for some method we have more hyperparameters.